Mm, mm, mm. How was the final review session this morning? Was it overwhelming? Was it a lot? Was it too fast for you?
Um, I slept in, so I didn't join
Uh-huh.
until like 10:30,
Oh
but
yeah.
no, it like felt okay. I think I'm just kind of rusty on like doing synthesis for like the
Mm.
older material. Like I was kind of rusty with like the epoxide opening.
Versus carbonyl, right?
Yeah.
So let's break that down here in depth, and then I'll give you practice statistical problem, and then I'll do it with you, show my thought process. And then after that, I'll give you another one where you are gonna show me your thought process, and then I can see any thing that I could provide feedback on from that. Okay.
Okay.
So epoxide opening, helix will tend to draw the epoxides in a flat bond like that without wedges or dashes shown on the epoxide like this, right? And usually I see him not include wedge or dash as well for these synthesis forms because that was a 118A thing. So he doesn't really care about stereochemistry like wedge or dash here as well. Um, right? So we're more concerned about the radial chemistry of this opening here. Like, is it going to be
Hmm.
on the more subcarbon or the less subcarbon? Right? Where both green carbon and purple carbon here are electrophilic because they're attached to this electronegative oxygen atom, making them partial positively charged, right? But in helixes 1s in B class, I do not want you to think about acidic conditions when you're opening up epoxides. I want you to think about basic conditions, which are going to be things with negative charge, like full or partial negative charge, right? And the examples of that for one it's in B specifically for Helix for the material here is either going to be alkyne anion like this, right? Because we saw that this carbon here is negatively charged, so that's the nucleophile, and because of that negative charge, this is in basic conditions right there. Now, the other thing is going to be uh, Grignard reactions, which is a one is in A reaction, but it's relevant for one is in B as well, right? So when you see an RMGBr like this, the carbon directly attached to the Mg is negatively charged. So because of that negative charge, this is also a base, right? So know that alkyne anions and Grignard reagents are bases.
Hmm.
Now, in bases, we would attack the carbon that has less steric hindrance, the carbon that has more space, right? So that's going to be the purple carbon here, right? So for alkyne anion, we're going to attack this purple carbon, making a new bond between the red star and purple dot. Um, And we have to break that epoxide open, giving the two electrons on this bond onto that oxygen right there, giving that oxygen a new pair of electrons. Now for stereochemistry here, like this will be inverted because we're doing a backside attack, but I don't think it matters for this one is in B, but just in case. This is the reference base of the epoxide between the green carbon and purple carbon. This green carbon here has the original bond to the oxygen that already has two pairs of electrons, um, but it now has three pairs of electrons and a negative charge because of this bond right there, which went onto the oxygen. And then we just copy and paste the groups on the green carbon, which is an ethyl group, and purple and the methyl group. And then we make a neo bond between the red star and purple dot to show that attack. Right. So this right here will be the neo bond from that attack where I made that bond going down in reference to that baseline because we're inverting this bond that's up to go down because it's doing a backside attack mechanism, inverting stereochemistry. And this red star here is attached to this alkyne with a 1, 2, 3 propyl group coming out of it as well. So 1, 2, 3, just copy and paste that decoration over like that. We also see a methyl group on carbon 4, so draw that, oh, a methyl group on, uh, not carbon 4, but the purple carbon. So we draw that methyl group coming out of the purple carbon like that, right? Now, when we are done with this, that's it, right? We tend
Hmm.
to clean up the reaction by adding an acid workup to clean up the reaction and neutralize the negatively charged oxygen to become a neutral alcohol molecule like this, right? OH. Okay. Now, the important thing here for synthesis is that you know how the alkyne carbon here was the star, aka the nucleophile, and
Hmm.
we made a neo bond here between that carbon and this dot carbon right here, right? You notice how the alcohol is alpha to that dot carbon right there? That
Hmm.
shows that this alcohol came from an epoxide oxygen, right? Because if we were to break it apart, like let's say we break that new bond and we try to go backwards here, we know that the star carbon can be negatively charged with an alkyne anion like that. But for the dot carbon to have that oxygen right there, it would have to come from an epoxide like this because we know that we are gonna attack this red dot and break open the epoxide on the other side, which this oxygen here is gonna go on the other side, the adjacent carbon, like that, right? Which we could label as alpha, alpha, like that, to that red dot right there, right? So on synthesis, if you see a new bond and an alcohol is like on the electrophile, if it's not directly on the red dot, but it's alpha to the red dot, then you know that this came from an epoxide, where the base of the epoxide is going to be between the red dot and alpha carbon, where the alcohol is attached to, like that, right? Because this green one is that green one right there. And everything else would be decorations, right? This pink oxygen here would be this pink oxygen of the epoxide right there. Okay, nice. Now, if you were given, let's say, for example, this structure and you try to go backwards here in synthesis, for example, right? Um, let's say we had this, let's jump straight into it. My thought process here is that I see a new carbon-carbon bond being formed here. So one of these carbons here would have to be the star, one of these carbons here would have to be the dot, right? Now, the dot molecule will tend to be the one nearest to the alcohol. So we have this carbon and this carbon here. This carbon here is the one nearest to the alcohol, so that's going to be my dot, and this is going to be my star. And that makes sense because this can easily become a star, become a negative charge by deprotonating it, right? So there will be a cut right there because that is a neo bond. Now, did this alcohol come from a carbonyl or did it come from an epoxide?
Mm. Carbonyl.
Correct, because it is directly attached to the dot, right? This is the alpha carbon in relation to the dot. If the alcohol was here on the alpha carbon instead, then this alcohol on the alpha carbon came from an epoxide, right? Which is this epoxide here specifically, like that, right?
Hmm.
So when we go backwards right here, retrosynthetically, which is what I always recommend, we know that this was an alkyne anion. That is what gives it a star, aka the nucleophile. The thing that will add on here, and the reason why I'm making this the intermediate instead of the carbonyl as the intermediate is because it's easier to go from here to here rather than from here to here. Right.
Hmm.
And then on the arrow, I'm gonna put first step is gonna be this dot here. And because that dot directly holds the alcohol, that dot directly has a carbonyl, which is attached to an isopropyl and a hydrogen. And a second step to clean the reaction acid workup with H3O plus. Does that make sense so far, Hannah? Can you visualize the mechanism
Yeah.
here? Right? That's good. Star attacks dot, pop that up there. O minus becomes OH with H2O plus. Nice.
Hmm.
Okay. Now the thing here to convert this terminal alkyne into this alkyne anion is a strong base. And the common strong base we use is NH2 minus, like that. Okay. Nice. But then to get to this alkyne right here, there are other reactions, which I'm gonna give it to you here now. And we're gonna use more reactions as well. And I'm gonna break that down with you. Let's say something like this, and then we are gonna have something like this, and then we also have something like this, and then we also have something like um yeah, let's keep it simple for now. Does Helix use that in 1:8 in these 1:8 reactions? I don't really see him do that, but I do see him do this right here. So let's stick with Helix's mindset of reactions here to be closer to the exam. Okay. So, okay. Okay. This one here, Hannah, is a little bit involved. This includes a lot of reactions from the beginning, right? But what's your
Mhm.
thought process here? I want to hear what you think about this.
Um, so like the first thing I noticed was the double bond
Mm-hmm.
um
Correct.
on the new. It's new.
Mm-hmm.
So I was
So
kind of
this,
thinking of how to get there
huh?
maybe.
Yeah. Are you thinking this is the new bond right here?
Yeah,
Yeah. So this double bond is new. Um, right? Um, so what kind of double bond is it? Is it a cis or trans double bond?
trans.
Trans, right. Now, do you remember what kind of reagent would create a trans double bond from what specific functional group?
Um, for the new stuff, a protected elid,
Mm, 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 mm.
Iliad or
Yeah,
something
yeah,
like
yeah.
that.
Wittig, you're thinking of
For
Wittig
Wittig.
reaction. Yeah, yeah,
Yeah.
yeah. Yes, 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 yes. So you can do that. That's interesting. I wasn't going for that, but let's try that because there are multiple routes, right? But
Hmm.
you know how it's an E or transalkene right here? For the Wittig reaction, um, let me. This is good. This is good. You brought this up. So there's two types of Wittig reaction. There is a type where you have aldehyde or ketone because chapter 17 and 18 are talking about aldehydes or ketones. Right, I was gonna say carbonyl, but carbonyl was way too generic, right? Because like a carbonyl could have been a carboxylic acid or acyl halide, something like that, but that's way too generic. But it's gonna be an aldehyde or ketone plus an ylid, and the ylid here could be either unconjugated or conjugated. If you have an unconjugated ylid, right? Let me make it like this to make it more clear. What kind of alkene would you get versus if you had a conjugated ylid? Con
The conjugated illid gives you the trans one.
yes, correct. Conjugated ylid gives you the trans one, and we don't want to be specific to trans because trans and cis can only be used for di-substituted alkenes, so alkenes with two substituents, right? But the ylid here can have more than two substituents. It can have three or four, right? And the alkene that we form could be like three or four. So we can't cis or trans there, but we can use E or Z, right? So the conjugated ylid would give you an E alkene. Um, and then the unconjugated ylid would give you a Z alkene, right? So let me give you an example right here. Let's say we have this molecule reacting with let's say this molecule over here. Okay. Now,
Mhm.
to predict the product quickly here, I want you to locate the carbonyl carbon, which I'm going to color code in blue, and the ylid carbon, which I'm going to color code in pink. There will be a double bond between them, where the carbonyl oxygen will go away, the PPH3 will go away. right? So I'm just gonna to predict the product quickly here. Draw that double bond between the blue carbon and pink carbon. That's the very first thing I would do for Wittig reactions, right? Because I know there will be a double bond between the carbonyl carbon and ylid carbon. Now, to determine if it's an E or Z alkene, I look at the ylid and see if it's conjugated or unconjugated. Is this ylid conjugated or unconjugated?
No.
Right. No. Right. I try to trick you here, Hannah. Right. Because this part here is conjugated, right?
Hmm.
But this ylid bond here is not conjugated. It's separated by this sp3 carbon right there. Right. So because it's unconjugated, we're gonna go for the Z alkene. Right.
Hmm.
So I know that my alkene here is gonna have two groups coming out of the same side like that. Right. The pink carbon here is attached to this group, so we just copy and paste that over like this. And then the blue carbon has this ethyl group, which I'm gonna draw out like that. So this is how you predict the product quickly, right? To summarize, first thing, make a double bond between the carbonyl carbon and ylid carbon. That's the very first thing. The carbonyl oxygen goes away, the phosphorus triphenyl goes away, and then the second step is to determine if you're making a Z or E alkane. Yeah, depending on the ylid. Is it conjugated or unconjugated? Right.
Hmm.
Nice. Okay, so we have an E alkene here. So let's stick with everybody. This is interesting because I wonder if this works. What carbon do you want to make the carbonyl carbon? What carbon do you want to make the ylid carbon?
Um, I want to make the carbonyl carbon, the one on the chain, like not in the cyclopentane, the next to the BR, the middle one.
This one right here?
Yeah.
Yeah. So let's say this is the carbonyl carbon in blue, and let's say this is the ylid carbon in pink. To go backwards here, we make a cut between them because we know that that bond was not there before, right? So let's say we go backwards right here, and on the reactant, we had carbonyl like that, which is specifically an aldehyde because we have a hydrogen here as well. But I'm gonna draw
Hmm.
explicitly because we usually draw hydrogens on aldehydes explicitly like that.
Hmm.
Now, that's the blue carbon right there. The pink carbon would be the ylid carbon, which would be double bonded to a phosphorus triphenyl group. Um, and because this is a E alkene, we want this to be conjugated. And to make this work here, I'm actually gonna put the carbonyl here because I want this to work because this is interesting. But I'll go back to that problem where it wasn't there, and then I'll show you what I was intending it to be instead. Okay?
Okay.
Right. But this is gonna work now because this ylid here is conjugated with this carbonyl, right? It doesn't have to be conjugated with an alkene. It could be conjugated with a carbonyl like that, or even an alkyne like that, right? Any pi bond. Okay, it's good. One, two, three. One, two, three. E alkene. Now, this is good because this brings a reaction that I did not intend to use, but it's gonna use one of the midterm one reactions here. Okay. Now, what is your thought process on how to get from here to here?
Um, Wait, let me get my note card out.
Yeah, yeah, that's good. Find that on your
Okay.
note card so that you get used to it on the final.
Um,
I could help you. I could ask you questions to guide you.
so we got an aldehyde. So I would do is it the hydroboration oxidation? Is that the one with the cyclo 2OH, and then the second
Hmm.
step is H2O2 and NaOH in water?
Hmm.
I'd do that.
Yeah, and that would get an alcohol product instead. So let's say this came from an alcohol like this, right?
Uh-huh.
Um, and then you could do 118A or like the like and you're a transfer student, so oxidation of alcohol.
Hmm.
You learned this already, right? In your other OChem class,
Yeah.
oxidation of alcohol to aldehyde with PCC, not Jones, because Jones would make this into a carboxylic acid. Um, and then to get from here, you did uh hydrogen oxidation, and that would work if this right here was an alkene, where we add alcohol in the antimark position, the lesser position.
Hmm.
So first step would be like BH3, second step H2O2, NaOH, H2O, like that, right? And now there is a tricky thing here because you know how we're missing a carbon here? So it's kind
Mhm.
of hard to cleave that oxygen, that carbon off right there, like that, right? So I'm trying to think of a way where we can do this. Yeah. Right. So we'll scratch that right there because of this problem here, right? Um, but you notice how here we're missing a carbon anyway. Like, if you count the carbons coming out of the ring, we have a two carbon chain coming out of the ring. But if you look at this carbon here, there's only one carbon, right? Now, think of Minton 1 alkene reaction. What reaction do you know that cuts up molecules and chops up one carbon, right? And adds a carbonyl in the middle.
Ozonolysis.
Ozonolysis, right? So um, we can do ozonolysis right here by saying that there was a double bond right here. And the first step we do O3. Second step we do like dimethyl sulfide here for ozonolysis, where we cut the double bond in half and put oxygen in the middle like that, leading us to this here. And the side product would be like that, which you can include, but you don't have to, right? Because this is the thing what we want to get this final product here. Okay, does that make sense so far, Hannah? Right?
Mhm.
Because we see that we chopped up one carbon right here, which left as a formaldehyde here. Okay. Now, how do we get from here to here?
Um, I thought of doing Hoffman twice.
Yes. So we could do LDA to get the less substituted. One, two, three, four. Yeah. So in this case right here, like this alkene would be equally substituted as this alkene, which would be equally substituted as this alkene right here. So it doesn't matter what base you use here, but to be selective, let's add this so we can have this in high yield. So then when we add those right there, we can use Hoffman reagent LDA, bulky base, to get the less substituted alkene instead of the more substituted alkene. And then to do Hoffman again, we need a good leaving group, right? Like bromine. So do you want to add a good leaving group here or here to eventually get us to here?
The less substituted one.
Yeah, because that shares it with that right there. How can we add a bromine on the less substituted carbon there?
Um, HBr and ROR.
Yes, radical hydrobromination would add bromine on the anti-Markovnikov position. So I'm saying these terms because you can see that these terms show up on the final, right? Anti-Markovnikov, right? Like that. And then from here, you could do LDA again to do E2 Hoffman, like you said, to get this less substituted alkene, like that. All right. And that's good. That's good. That's good that you thought about that Wittig reaction because like th that could very well be on the synthesis as well, right? So to summarize this whole synthesis problem, the first thing we did was E2 Hoffman, and then we did radical hydrobromination, and then we did E2 Hoffman again, and then we did ozonolysis, and then we did the Wittig reaction with the conjugated ylide to get the E or trans alkene here, like that, right? So this is a old material. This is Minton 1 material. This is old material. This is Minton 1 material, and this is chapter 17, final material. Okay. Now I'm gonna show you the synthesis that I intended to give you here, right? Which is going to be this, getting into, whoa, no, 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 no. There is a separation here. CH2, like that. Yeah, okay. No, one, one, two, three, six, yeah, one, two, three, six. Okay. And then I want you to make this that, and make this that. This is what we had originally.
Mhm.
Now, the first thought process you had was an Wittig reaction with a ylide and carbonyl, but if we had this, we cannot do that. Because if you look at the alkene, this is a trans alkene, an E alkene, which comes from a conjugated ylide, right? And if we break this apart and say like this is the ylid right here, this is not a conjugated ylid. This is an unconjugated ylid because of this sp3 roadblock right there, leading you to um, cis alkene,
Hmm.
right? Now I'm gonna go back to this and fix what I just said, right? Because you can still technically do an ylid Wittig reaction, but because you'll get a cis alkene here, you can make this into a trans alkene. Wait, I'll show that after this one here. Okay, so the similarities and differences between this molecule and this molecule is gonna be uh like this highlighted yellow structure here is gonna be the exact same highlighted yellow structure over here, right? The new thing is gonna be this blue thing over here, and the new bond here is gonna be between these two carbons right there. That's the new bond right there. So one of this would be the star, one of this would be the dot. Which one do you think is gonna be the star? Which one do you think is gonna be the dot based on where the oxygen is near?
Um, the star is going to be the alpha carbon position next to the carbonyl, right?
Mm, and this dot star dot and then alkene. And then let's say this was an epoxide. And then there's an alcohol here. And then you convert this to bromine, you could get the alkene right there. This can happen, like this is a star, this is a dot, but based on what we have so far, um, like right here, right? Oh wait, actually, hmm, interesting. Yeah, that can happen as well. But I wasn't going for that. Uh,
Okay.
okay. Let's stick with your way and show you like it will work, but you have to go a different route, right?
Hmm.
Like there's so many routes here that you could do. But I want to show you it just so you could use it in synthesis. And you have more tools in your toolbox for synthesis. Okay? So if you make this the star right here and this the dot right here, and we go backwards. But actually, I'm going to show you what I intended to do first, so then it doesn't confuse me, and then I'll try to do it your way here. Okay?
Okay.
Okay. So you know how the alcohol is here?
Hmm.
It's close to this carbon, so I'm gonna make that the dot. Because you know how when we're talking about epoxides and carbonyls, the oxygen is nearer to the dot, nearer to the dot. If you know that the oxygen is like one carbon away or alpha to this dot right here, did this oxygen come from an epoxide or come from a carbonyl?
Epoxide.
Correct, epoxide, where the epoxide was like that. Right, and when we break open the epoxide, what does the epoxide become?
Um, an alcohol.
Correct. So that carbonyl there was an alcohol. What reagent can we do to convert that alcohol into the ketone that we want in the final product?
Jones.
Yep, correct. Jones or
When do you use
PCC.
Jones versus I'm like very, very rusty on the
Hmm.
118A stuff, and I like still kind of am confused when you use Jones versus PCC.
Hmm. Yeah. So Jones or PCC will only make a difference for primary alcohols, like this, right? A primary alcohol is when the carbon holding the alcohol is only bonded to one other carbon, right? So this is the alcohol, this is the carbon holding the alcohol. This carbon holding the alcohol is only bonded to one other carbon, considering this a primary alcohol, right? And the differences between PCC and Jones here is that PCC and Jones are both oxidizing agents, but PCC is a weaker one, Jones is a stronger one. And in organic chemistry, think of oxidation as the gain of bonds to oxygen or electronegative atoms, or losing the bonds to hydrogens, right? So when you oxidize a primary alcohol with a weak oxidizing agent, PCC, you stop at the aldehyde, right? Because this is the same blue carbon right there. That blue carbon traded a bond of hydrogen for a bond of oxygen. If you used a stronger oxidizing agent, Jones, the primary alcohol would go all the way to an carboxylic acid, where we trade two bonds of hydrogen for two extra bonds of oxygen. So we
Okay.
like oxidize this alcohol even further to carboxylic acid because carboxylic acid is a more oxidized form than aldehyde, right? And for synthesis, if you want to go from an aldehyde to carboxylic acid, you can do that with Jones as well. You cannot do PCC because PCC is a weak oxidizing agent. It cannot go to the carboxylic acid,
Okay.
right?
So that's the only difference, only if it's primary.
Correct.
Okay.
Because if you had a secondary alcohol and you did PCC or Jones, it does not matter what you use. You get the same exact product because this alcohol here that's secondary only has one proton to trade in for to become a ketone specifically, like that, right? If you try to make this a carboxylic acid like that, that's not good because this carbon here would break the octet rule. One, two, three, four, five. We can't have that.
Hmm.
Right. Um, if you had a tertiary alcohol, which is good to know, right, for synthesis, because if you have a tertiary alcohol, we see that this carbon here holding the alcohol holds no hydrogens. So we cannot trade in any hydrogen bonds for oxygen. So we cannot oxidize this tertiary alcohol. There will be no reaction. We can't oxidize tertiary alcohols because there's no protons on that carbon to trade in for oxygens, right? So secondary alcohol, no difference. Primary alcohol, big difference, depending on if you use PCC or Jones.
Okay.
Okay, nice. Um, so in this case, we have a secondary alcohol, so it doesn't matter. You can use Jones or PCC here.
Hmm.
Nice. And then we have an star right here because we know that this alcohol came from an epoxide, with making this the dot on the left subcarbon. And the star right here was a transalkene. And let's say that transalkene came from an alkyne because we can easily make the terminal alkyne nucleophile by making the alkyne anion. So let's say that was an alkyne before. Um, and it was still attached to this group right here. Do you remember the selective reducing agent that would selectively reduce this internal alkyne into the transalkene specifically? There were three.
Is it the poisoned
Mm,
one?
mhm. The poison one, Lindlar's catalyst, makes the cis alkene,
Okay.
whereas the dissolving metal reduction reaction with sodium metal and ammonia liquid, which is a radical mechanism, which you can get tested on, um, creates the transalkene, right? There are
Hmm.
three reducing agents here, H2PDC, the poison one, H2 Lindlar's catalyst, Lindlar's cat, and dissolving metal reduction, sodium metal, and ammonia liquid. If you're working with internal alkyne, this would fully reduce it into a single bond alkane. Lindlar's catalyst would make the cis alkene. Dissolving metal reduction would make the trans alkene. And depending on what you want on the synthesis product or intermediate, you would use a specific type of reducing agent. In this case, because we want a trans alkene, we're using this specific reagent here that would convert this alkyne into the trans alkene, like that.
Hmm.
Okay, nice. Now we can actually break this bond right here because you know how that bond wasn't broken, like going backwards, right? It was still there, still there, still there. We can now break that apart and show that before that was an alkyne anion, making that the star. And like the dot, like you said correctly, came from an epoxide, which this is the same exact dot right there. Because the alcohol has alpha to it or one carbon away from it, it is coming from an epoxide because we know that we attack the left subside, kick that up there, and the oxygen would go at the alpha carbon. First step, second step, acid workup, clean up the O minus to OH, like that. Right? And you can draw this entire structure on the arrow. That is allowed there. Okay. Now, how can we get from here to here now, Hannah?
Um, we want to do, would it be doing like E2 Hoffman twice
hmm
again and then doing Br2 CCl4?
Yes, correct, correct. Hoffman one time would correct the alkene on the left sub right there. And then we do radical hydrobromination with HBr and Bror to put bromine on the anti-Markovnikov position right here. And then from there, we could do LDA again to get the Hoffman alkene again right here. And then from here, we are gonna do the Br2 CCl4 to get two good leaving groups vicinal to each other, aka adjacent to each other, on the same carbons of the alkene. So Br2, A product solvent CCl4. Don't put water or alcohol. That's different reaction. Okay, A product solvent, that. And then from here, you could get directly to here by putting NH2 minus excess amount, but you need three equivalents of that. Because the first equivalent would create a double bond, get rid of one good leaving group. The second equivalent would create the terminal alkyne. The third equivalent would deprotonate the terminal alkyne to get the alkyne anion, like that. Right. So to summarize this whole entire synthesis, E2 Hoffman, radical hydrobromation, E2 Hoffman, halogenation of alkene in a product solvent with no nucleophilic competition like water or alcohol. Um, terminal alkyne formation and then alkyne anion formation by doing acid base with the third equivalent of the base right there. So double elimination and then acid base. Opening up epoxide in the less carbon in the basic conditions. Dissolving metal reduction to get the trans alkene, and then oxidation to get the carbonyl from the alcohol. Now, for helix synthesis problems, you will not get 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8 reactions. You will get between 3 to 5 reactions. 3 to 5 reactions,
Mhm.
right? But this is good comprehensive review here. Okay, do you want to try your way on what you said earlier? What was like if you switched up the roles here, like if you said this was the star, this is the dot, right? Because that can happen right there, right? And I said earlier, oh yeah, I think I know what you said now. So let's say that happened right there, which is possible. This is still going to give you full credit, right? This is good to know because you can keep this in the back of your mind for the synthesis on the final. Okay. Um, so let's say the roles were reversed. Let's say instead of having, yeah, let's say this is a star, this is the dot. This is the neo bond between the star and dot. This is this structure here. Okay. Okay. If this is the star right here, aka the nucleophile, you notice how it's on the alpha carbon right there? This is going to go to
Mhm.
chapter 18. Is it on the less or more sub-alpha carbon? Because there's two alpha carbons here.
Um, they're equally substituted, right?
Yeah. They are equally substituted. What I should have said is like, let's say this bond was broken. The new bond between
The less substituted.
yeah, correct. Right. Nice. Right. This is the alpha carbon here, this is the alpha carbon here. So if we go backwards here, right, and we want the less substituted alpha carbon to be the nucleophile, what kind of base would we need to include? The reversible or irreversible base?
Irreversible.
Right. And the thing that you're going to use for that is LDA, which is going to
Hmm.
create the nucleophilic carbon at the less subcarbon like that.
Hmm.
Right. Now we want to make this electrophilic right here, but we can't put like just a bromine right there because we can't do SN2 on an sp2 hybridized carbon like that.
Hmm.
Right? But what we can do is that where do you think this alkene could have came from? What kind of reaction creates alkenes? Right? Think of old material 118A or like the Minton one reaction. Like we talked about this early already in the previous example. E2
E2 Hoffman.
Hoffman, right? And for it to be an E2 Hoffman, we need a good leaving group,
Hmm.
bromine like that, right? And that's gonna give us this here. And now from this point, let's say we already have this carbonyl like that. Uh, and then Yeah, yeah, that works because this is less substituted than this. That's good. Right? Where this was the star, this was the dot. Now, you know how this is a star, this dot making this new bond right there?
Hmm.
This bromine right here is alpha to this dot. So if that's the case, what do you think this bromine was before? Like if it's alpha to the thing, think of carbonyls or epoxides here. Like if a group is alpha to the dot, will it most likely come from a carbonyl or would it most likely come from a, a epoxide?
Epoxide.
Correct. But what does epoxide create? It creates alcohols. So that bromine was an alcohol before, like that,
Hmm.
right? Where this is the star, this is the dot, and we know that the alcohol is alpha to the dot, so we know that this was an epoxide like this. Right. Now, the reaction that creates the bromine here is PbR3. Are you familiar with that reaction, Hannah? PbR3?
No.
Converting alcohol to bromine. Okay. Yeah. So the reason why we don't do HBr here, which is gonna like protonate the alcohol to become good leaving group, is because it leaves from a carbocation, hydride shift, carbocation goes here, the bromine would go here on the more sub position, but we don't want that, right? So PbR3 would just convert the alcohol to that position, convert the alcohol to this bromine here, and now we could break this apart and actually give us an epoxide here now, right? Uh, Epoxide. And we know like the reagent which we found earlier is going to be this with LDA because that would make this less sub alpha carbon to the nucleophile, this less sub epoxide carbon to the electrophile, which is what we want to create that new bond right there. Uh, like that. Okay.
Mhm.
Now, do you know the reaction that creates epoxide, Senna? The reagent, I mean, that creates epoxides. Let's say the epoxide base was an alkene. Right? Let's say this was an alkene right here.
Oh, MCPBA.
Correct. MCPBA, that 1, 2, 3, 5 letter reagent creates epoxides from alkenes like that. Okay. Now, we already did this multiple times. How can we get alkene here?
E2 Hoffman
Uh-huh.
and HBr Rohr and then E2 Hoffman.
Yes, 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 yes. Right. That's good. LDA, HBr roar to give us a bromine on the left subcarbon, and then E2 hopping with LDA like that to get this alkene on the left side, MCBA to epoxidate that alkene. And then we use this is the chapter 18 stuff here that's gonna be very useful for synthesis. We want the alpha carbon of this specific ketone, aka the less alpha carbon, to be the nucleophile. So we use an irreversible nucleophile LDA to make that the star. And then it attacks this epoxide. Once it has that enolate ion, break that up where we have the alcohol alpha to this dot, and then we do this 1:A reaction, which I don't think Helix will put on the synthesis, but that can convert the alcohol into the bromine directly without worrying about any hydride shifts. And then we do LDA again, just to get that alkene on the left subcarbon right there. Right. So this right here, technically, like can be on the exam, but I don't think so because it's like way too involved, like more than 5 reactions here. But this is one is in A, one is in B, one is in A/B because this was introduced at the end of one is in A, one is in A, one is in A, and one is in A. So mostly one is in A here. But the biggest one is in B reaction here is gonna be this chapter 18, uh, alpha alkylation on the less sub alpha carbon and radical hydrobromation. This right here, a lot of students would like forget about from midterm one.
Hmm.
From midterm one, right?
Hmm.
That's good. Um, okay. Now, I'm gonna put a caveat here because you know how this is a strong base LDA and it's gonna look for the most acidic proton. This is assuming that this LDA here is gonna grab that proton, make that double bond there, kick that bromine out to get this final product here. But you know how we also have these alpha protons here that are also acidic?
Hmm.
To protect these alpha protons here from being getting deprotonated and forming the enolate ion here, do you know how we could protect this carbonyl here?
Um,
So this is good for synthesis as well,
um,
for chapter
I
17.
don't remember the name of it, but
Uh-huh.
it's
Uh,
the one with the water, like that has the R group attaching to.
uh-huh, correct. To create this hat-like structure, this diol, two alcohols, would convert the carbonyl into a cyclic acetal. And it's a cyclic acetal because it's in a cycle, right? It's in a cycle and has two OR groups, OR, OR, like that. Right. So to make this into more high yield, which we can do, um, uh, with chapter 17 reactions now, which is good for the more relevant for this material, we can now do E2 Hoffman without worrying about these other alpha carbons because there's no carbonyl here. Right. I didn't show you this when I was going over it because I didn't want to overwhelm you because there is a lot of things going on here. Right. But this is why we need to do protecting group because we do not want to touch the alpha carbons of this carbonyl here, right? And then boom, 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 boom. And then do you know the reagents that would deprotect the carbonyl and go back to carbonyl here?
H2SO4 and water.
Correct, acid and water. And the name of that reaction specifically is hydrolysis. We're going to do hydrolysis to convert the cyclic acetal back to the carbonyl. Reverse mechanism in acidic conditions. Mhm. Converting this cyclic acetal carbon in pink to the pink carbonyl. Nice. So this here is required to get high yield because if you don't protect it and you do LDA E2 Hoffman right away here, you won't get the product in high yield because there's this proton to get, right?
Hmm.
Nice, 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 nice. So we had a protecting group here as well. Okay. Is this helping, Hannah? Like with the
Yes, I think
comprehensive
so.
cumulative
Yeah.
review? That's good. That's good. So we did a lot of midterm one, midterm two, alkane synthesis reactions. Chapter 17 with the Wittig reactions, and chapter 18 with the LDA and irreversible kinetic alpha alkylation under less carbon. There's one thing missing that we haven't talked about for synthesis, which is EAS, like the benzene reactions with liquid,
Mhm.
the meta director. So I'll try to create one that involves alkene, alkyne, benzene, and chapter 17, chapter 18 together.
Okay.
So it might take me some time, give me like 3 to 5 minutes, and then we'll break it down together.
Okay.
It's gonna be a mega one. And there might be some problems because you know how like we might protect some of the groups and there's might be other groups like that are susceptible. So bear with me here. I'll try my best to make it clean. Right. Okay.
We didn't get that one.
Uh
You had to calculate something. Yeah. Well, I mean, we kind of did. I heard this one was really, like the one we had was easy. Yeah. Because it was just the triangle, the same triangle on both ends. So that when you have to do was x squared equals 15 squared, like the first they gave us.
Okay, Hannah. Let's try this comprehensive review here.
Okay.
Wait, I forgot an alkyne reaction. There's alkene for sure, benzene for sure, chapter 17 for sure, chapter 18 for sure, but the alkyne one, let's see, there's no alkyne here. But what I can do is I can um do this right here. Alkyne, alkyne. Um, okay, let's try this. Let's try this, Hannah. Let's try this here.
Okay. Okay.
You're actually the best person. I have making my note card next to. What was her final class? Was it similar to the summer one she gave?
Yeah, honestly, like, yeah, you should expect the same thing. Like, I think she was one actually some, like one long mechanism. Yeah, it's only ever like 5 minutes. No, but it's like, I'm trying to remember if it's kind of bad. I think it's bad.
Does the chart come back to selectivity? You know, like where it's like tertiary versus secondary, primary, and like it's like not fluorine. Oh, it's fluorine, chlorine, and
What's your thought process so far, Hannah?
I noticed that there might be aldol condensation because the double bond.
Yeah, so outer condensation creates alpha beta unsaturated carbonyl. There's a double bond here, but nearby we do not see any carbonyl. There's no carbonyl. So that's good. I should include that here. I should have included that here. Yeah. So this one here would not include aldol condensation, but that is very well might likely be on the final aldol condensation on the synthesis. Right? But there will be other chapter 17, 18 reactions here.
I want to make like a whole list.
Okay.
I'm gonna highlight the similarities between the two. So let's say that the yellow highlighted structure on the reactant, which is this entire thing right here, is gonna be this entire thing right here, like that, right? Where we see that this is a new group, and this whole entire thing is a new group right here.
I might watch them open the break, so I'm not lost.
Right. Now I'm gonna ask you guiding questions here.
It's like purely just reactions. From now on, you just be learning different types of reactions.
We see that there's a benzene here and a benzene. Oh, there's no benzene here yet, right? Because there's no double bond here.
So I think this week, it's like self-learning, like without any pressure.
So let's look at this group here. What's the most activating group on this benzene ring? We have
The alcohol?
yes, correct. And is alcohol orthopara directing or meta directing?
Orthopara?
Orthopara, right. We already have this group attached, so we don't have to worry about that. We do, however, have to worry about this group though. And we did you see that this group is ortho to this alcohol? So we do not want this group on the para product. What can we do to block off the para position here?
Do sulfonation.
Yeah, through sulfonation, correct. So we know we're gonna have to do sulfonation soon to protect that. Okay. But first, let's try to get our benzene ring. How can we get our benzene ring here?
My bad. Yeah, watch out stuff.
I actually don't know.
Yeah, so to get a double bond, we know we can do elimination. right? And do we know there's a proton right here?
Oh yeah.
And then we could do like, let's say for example, NaOH, OH minus will grab that proton and make a double bond like that, restore aromaticity, right?
Hmm.
But there's a problem because there is a more acidic proton, which is this alcohol here.
Hmm.
So we have to protect that alcohol using this alkene and H2SO4, which will create the ether first. Okay. Now from here, right? We can, or we do not have this alkene yet. Now we can do the E2 reaction with NaOH and water, which would form that benzene without worrying about the alcohol proton, like that. Okay. Now, let's look at this over here. Let's look at this group. You know how we added a new carbon-carbon bond to this benzene? The reactions that would make a new carbon-carbon bond is Friedel-Crafts alkylation or Friedel-Crafts acylation. So now we have an alkene here. Is this an E or Z alkene?
Z.
Right.
E.
So E, correct. Because this carbon here, this is the highest priority group compared to the isopropyl.
Yeah.
This carbon here, this is the highest priority group compared to the hydrogen. So it's E alkene. So what reaction do you know that can make an E alkene in chapter 17? Think of chapter 17 reaction.
The Wittig.
Wittig reaction, correct. And because it's an E alkene, do you want a conjugated ylid or unconjugated ylid for E alkene?
Conjugated.
Conjugated ylid, correct. So one of these carbons here will be the ylid, one of these carbons here will be the carbonyl. So what do you think is going to be the carbonyl? What do you think is going to be the ylid here, based on what we have?
The carbonyl one is going to be the benzylic position.
Yeah, well, correct. So if you were thinking about which carbon would be conjugated for the ylid, right? Both would be conjugated because let's say there was no bond there, and let's say you have PPH3 here
Yeah.
and PPH3 here. Both are conjugated, right? But we want it in a way where it's easy to add the carbonyl, right? And we know Friedel-Crafts acylation as a carbonyl to the benzene, like that, right? So I'm gonna say that like how we did earlier to be consistent. This is the ylid carbon, and this is the carbonyl carbon, like that, right? Nice. Okay. So we could do Friedel-Crafts acylation here now because we have two groups here. Um, but before that, we want to block the para position. How can we block off the para position here?
Sulfonation.
Yep, sulfonation. With SO3, H2SO4. And I just realized the alkene would be destroyed in acidic conditions. So that's why that's a problem. But what we can do here, right, is we could protect the alkene. Let's protect the alkene first before we do that. So the alkene is not protonated by the acid. We can protect the alkene by doing, let's say, I'm just going to put HBr here. HBr. And that would put bromine on the Markov-Markov position. And we could get the alkene back by doing LDA. And then when we do SO3, H2SO4, we're gonna protect the para position. SO3H. This bromine is untouched by acid. This ether there is there. Then we do Friedel-Crafts acylation with this carbonyl we want. AlCO3. And you know how OH and NH2 are strong nucleophiles? If this was an OH right here, the oxygen would attach to the acyl group. But we don't have to worry about that because we already protected the OH into the ether, like that, right? So now that would go into the ortho position relative to the strongest activator, like this. Which is gonna be like this. Br. This is supposed to be Cl because we're doing acylation here. ether, add that group there, boom, boom, SO3H. Now from here, let's jump straight into Wittig reaction, right? We already have our Wittig structure, what that's supposed to look like, which is this pink carbon with the benzene. So benzene, and it has to be conjugated, so it will be conjugated to get the E alkene, which will give us this E alkene here with this ylid structure, and this benzene with that. Boom, 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 like that. Before I do the step though, I want to get rid of the sulfonate group with dilute H2SO4 in water, because if I don't do that and I have this with the SO3H still on it, and then I do dilute H2SO4, this alkene will be destroyed. And I do not want to destroy the alkene. I want to keep the alkene for my final product. So to prevent that right there, I'm just gonna get rid of my SO3H group like that. So notice how like when you get into big synthesis problems like this, like stuff like that can get in the way because other stuff can react with the acid, right? Um, Br, and the SO3H group is now gone, right? Okay, and now I could do the Wittig reaction without worrying about that SO3H group. It's still there, and then we have this bromine here. Okay, and now from here, let's get this alkyne by doing LDA, which will create an alkene on this position here. Right? And how can we create an alkyne from an alkene?
With Br2 and CCl4 and NH2 in excess,
Yes.
NH3 in excess.
Yeah, that would create the terminal alkyne anion. Correct. Okay. I've never made a synthesis problem like this before, Hannah. This is my first time like creating a comprehensive synthesis problem for the course. But like think of it as an exercise problem, like thought process, right? Because you will not get something like this on the final. It's just for me to like try to include everything for you, right? LDA would create this alkene here. Nothing else would be affected by the LDA. You have to ask yourself that. Alkene is not affected, ether is not affected, benzenes are not affected, right? So because of that, we're gonna look for the most acidic proton, which is this here, to create that double bond. And then, like you said, we're gonna do Br2, but we do have an alkene here, so that's a problem. So see, like you know how you said Br2 and CCl4? We have two alkenes here.
Yeah.
Right. So before that, right? How did I protect the first alkene? What did I do to protect this alkene here?
HBr.
HBr, right. But I don't want to use HBr here because this is gonna go into conceptual 119A. If I do HBr, BR would go into this position, the Markovnikov position, right? And then when I do LDA, LDA could have made this alkene back, right? I want to use a worse leaving group than Br. Right? What's a worse leaving group than Br?
Alcohol.
Alcohol is a worse leaving group than Br. So what can we do to put an alcohol on this position here? Or you could put it in this position, doesn't matter. You could put it in either or, the more or less of position. So
Hydrobromation or no, hydroboration oxidation.
Yep, which you put alcohol on the less of carbon, right? So first step BH3, second step THF, second step H2O2. So this is another alkene reaction. So that's good that we're doing this. NaOH, H2O. Now, when I do LDA here, what's the problem? What's gonna get in the way of us getting this proton and making the double bond? What's another acidic proton that's more acidic than that?
The alcohol.
Yeah. How can we protect the alcohol?
Um,
This
with
alkene, H2SO4, the same way
yeah,
as how we protected the alcohol in the beginning,
yeah.
right? And then that works out because we can deprotect both alcohols with the same reagent here. So a lot of protecting groups here because there are a lot of things that can react with this because that's the con of making this comprehensive synthesis problem. There are other things that can get in the way. So that's why we have to use protecting and deprotecting groups like this, right? And now we can use LDA without worrying about anything else here, right? And that would create the alkene here. And that's the only alkene that's reactive. And we don't have to worry about any other alkenes getting in the way as well when we do Br2 CCl4, right? Now we could do Br2 CCl4, like you said. Now, you already know this, so so just to save space here, right? First step, Br2, CCl4, add two bromines on those two carbons. Second carbon, excess amount of NH2 minus, right? And then what would that do? That would create an alkyne anion that's negatively charged, right? Now, for that alkyne anion to be negatively charged right there, um, uh, we add this new OR group by adding a primary halocane like this, like that right there. Does that make sense so far, Hannah?
Yeah.
Right. So don't do that on the synthesis. Like actually draw out the intermediates for each because that's graded, but I'm doing this to save time here because this is a big synthesis problem here. Right. And then that would give us this terminal alkyne with this group right there. Nice. Okay. Now we want to get an alkene here and convert this to an alcohol. To do that, we can use concentrated HI, and that would do multiple things here. That would deprotect the two ethers back into the alcohol, right? Because that's a deprotecting group for ethers back into the alcohol. But you know how we have an acid alkyne? If we have excess amount of HX here, this is another alkyne reaction. So I'm glad I'm including this alkyne here, right? Because before I didn't have an alkyne, but now I have a lot of alkyne reactions. What do you think is gonna happen between the alkyne and excess amount of HX here?
I don't know.
So if we think about this, like let's say terminal alkyne like this right here, we react with let's say HBr, right?
Hmm.
Alkyne will get protonated by the HBr, get this carbocation on that position, and then Br attacks it, and that becomes this right here, right? Um, and then we don't stop there because we have another alkene, which the alkene can get protonated by the HBr, kick that out, form a carbocation where the bromine was, and then the second equivalent of the bromine minus attacks it to become this bromine right there, like that.
Hmm.
And that messes things up because like I don't want that. I do not want that at all. So we have to protect this alkyne somehow. Uh, the way that we can protect this alkyne here is let's make it into a let's make it into a cis alkene with H2 Lindlar's catalyst. H2 Lindlar's cat to make the uh alkyne into a cis alkene. Now once I have the cis alkene right here, when we do a concentrated HI, the alkene will still react with the HI. The alcohols will be deprotected into the alcohols. Like this. Right? So this will become alcohol. This will become alcohol. And then the alkene here will also react with the HI, right? And the iodine here will specifically go on this carbon. They look like they're both equally substituted, but this is where it would go to because you know how in the intermediate there is a carbocation intermediate. The carbocation is more stable here at this allylic position because it's right next to this benzene ring right there, like that. Right? Compared to this carbocation over here. Okay? We're getting closer and closer. Oh no. I'm running out of space, Hannah. I'm gonna make it really small, okay? I'm gonna zoom in.
Okay.
Uh, I want to make this double bond back, and I was thinking of doing H2SO4 and water to do dehydration of alcohol, but that would make this alkene here.
Oh.
Right? Which
Uh-huh.
we can do. Let's say we do that because we could get that desired alkene back. Okay, this is going to be very small, but you can zoom in when you review the notes again and the recording of this, as I explain this for you, which I'll send to you privately. And then ungroup that. And then we know that alkene is going to be right here because that's the more substituted position. We want to get this alkene right here, so we could do HBr roar. Which will put a bromine on the less sub position. And then we do LDA to do E2 Hoffman. What the? Okay. Okay. And then now, like we said, LDA. Get this into the position we want, which I did not think of this reaction steps when I created this, but that is that. Now we want to make an alkyne back into here, which we can make an alkene and an alkyne, but we want to do like Hoffman E2 or Zaitsev E2, doesn't matter here, because there's only one alpha carbon there. But there's a problem because there's an alcohol here, which we can protect with acid and alkene, but the acid will destroy the alkene. So before we do LDA right here, we're gonna protect the alcohol one more time with this alkene H2SO4 and give this an ether. So this is good practice, good exercise for you to know when to use a protecting group or not. You always have to be on the lookout for other functional groups, other acids or bases that may interrupt with the thing you want, right? Don't just hyper focus on one thing. Look at the overall structure and see what is also going to react when you do the synthesis here. And if the other thing reacts, but you don't want it to react, you can protect it and then deprotect it at the end, like the para position or alcohol, or in this case, alkene. Or yeah, in this case, alcohol. Yeah, yeah. What was I doing? I was protecting the thing, alcohol with that. This is gonna be here. And now we do LDA to get this alkene right here. And then from here, oh yeah, this right here is still a bromine. And I'm gonna put one equivalent of the LDA here to show that it can only react with one thing. All right, we have iodine uh versus a bromine leaving group. The iodine is a better leaving group because it's bigger. So it's gonna kick out the iodine versus the bromine. Another reason why it's gonna make an alkene with the iodine instead of the bromine is because if you look at these protons here in green versus purple versus blue, the green one is the least substituted one. It has the least steric hindrance for LDA, and we only have one equivalent of LDA to make that alkene right there. So that bromine will still stay there. Okay. And then from here, let's do LDA again. to get the alkene right here. Wait, actually, no, I want the alkyne. Let's get the alkyne with Br2 and because we did this work to do this first step, second step, NH2 minus, and we only need two equivalents here because this is an internal alkyne. 1, 2, 3, boom, 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 and then we have. Oh, this NH2 right here, let's not put two equivalents. Let's put excess because that base right there, right, will also do E2 reaction and get our alkene back. Let's go. Oh, I was worried. I was worried on how to get the alkene back. But this right here, I did not know. If we put excess amount, it would do elimination until we get to like we had two bromines here until we get the alkyne, and it will also do elimination to get this alkene here. But this is not very high yield, right? It's gonna be a low yield, but to fix that problem here, I'm gonna put that turbidal there, right? Because you know how like when we do E2, we want to get the more stable alkene right there, right? So I'm just gonna put a turbidal there, so we don't have an alkene right there. Oh shoot, that can't happen though, because that worked out terrible for that carbon. Okay, huh. Oh, I know what I could do. Instead of using NH2 minus, what can I use to get the less substitute alkene? What is the
LDA?
Hoffman? LDA, correct. So I could do LDA excess, and it would do the exact same thing. It would create
Okay.
the alkyne still, but it would not go for the more substituted alkene there. It would go for the less substituted alkene here. There's no protons here, so we don't have to worry about that.
Mm-hmm.
Good, good. Okay, so that's why the choice of base matters as well here. So this can still work. Are we close? We are close. Get this back into the ether using alcohol using concentrated HI. But there is a problem here. So this is not a very good synthesis. It's going to get you low yield because there's a lot of questions. And the strong acid here is going to react with both alkene and alkyne. But then like we're just going to go in a loop of protecting, deprotecting, protecting, deprotecting. But I think we got the point here, right? Right?
Mm-hmm.
Like we could just deprotect this with concentrated HI. Let's put dilute here because you can put dilute to show that there's only a little amount which will only react with the ether and convert it back to the alcohol. And you can do that for the synthesis and it will not touch the alkene and alkyne like that.
Mm-hmm.
Okay, to get this here. Okay, so that includes alkene reactions, alkyne reactions, benzene reactions, protecting groups, right? Wittig reaction, chapter 17, chapter 18. Not many chapter 18 reactions. Like no Aldol is a possibility, like you mentioned, and Robinson annihilation. Okay.
Mm-hmm.
I'll send you the recording of this and the notes of this to you right away, Hannah. And on the school, the session 1 recording and notes already uploaded, and then the recording of part 2 this morning will be there today as well.
Okay.
Yeah.
Thank you so much.
Of course, Hannah. Are you feeling much better now about the cumulative synthesis?
Yeah, I feel a little better.
That's good. So just to summarize what I would do, find the similarities and differences between the reactant molecule and product molecule, like highlight it or like do whatever, visualize it, the similarities, locate the new groups, see how you can get those new groups by going backwards retrosynthetically, meet in the middle, and then you see that you can do that with 3 to 5 steps for helixes exams,
Mm-hmm.
right?
Okay.
Yeah.
Yep.
Of course.
Thank you.
Yeah. Good luck on the final, Hannah.
Thank you.
Bye bye.